Hi everyone, my name is Zhu Junhao. I come from National University of Defense Technology. The topic of my presentation is HDNH, array efficient and RAID optimized hashing scheme for hybrid DRAM-NVM memory. The outline of my presentation is as follows. The first part I want to introduce is the background of this research. With high memory density, number volatility, and DRAM scaled latency, NVM brings evolution to storage systems and durable data structures. NVM speak up storage systems such as TB scaled memory for applications and instant recovery from system failures. And Intel obtained DC, the persistent memory module AEP, the first commercial product of NVM, shows some new features that are different from the previous assumptions. Higher read latency, lower bandwidth, and block access granularity compared with DRAM. It is reasonable to build up hybrid memory to give full play to the complementary advantages of DRAM and NVM. NVM index structures are important for the large-scale storage systems to provide faster queries. Tree-based structures and hashing-based structures is currently the most commonly used index structure. Hashing-based structure achieve O1 the time the complexity for point query. Hash index is widely used in databases such as Redis and Memcached. In the second part, I want to introduce our motivation. The first problem is that multiple accesses in NVM for probing data. Existing the hashing scheme usually use multi-thread bucket to resolve hash collections. Searching a bucket typically requires a linear scan of the slots. One or multiple buckets in NVM have to be searched to find out if a key exists. The second problem is hotspot issues for searching. Alibaba observes that 50% to 19% of accesses only touch 1% of total data. It will cost longer access latency and waste NVM bandwidth for this hot data. So we can employ cache to store the hot dataset in the DRAM. The third problem is cross-grade lock for concurrency control, such as segment reader-writer locks for queries, and bulky level locked for concurrency. Heavyweight concurrency control can easily exhaust Navan's limited bandwidth. The third part is our design of HDNH. First, we can see the structure of HDNH. HDNH sets up a two-level structure in Navan. The top level has two M segments and the bottom level has M segments. HDNH chooses segment as the hashing the unit and it places optimistic compression vectors. We call it OCF and the hot table in DRAM. We propose optimistic compression filter OCF. OCF reduces excessive Navan access for propping data, and it uses fingerprints to filter out unnecessary Navan reads in the DRAM. It properly configures data and metadata into hybrid memory. And HDNH uses hot table to solve the hot spot issue for searching. Hot table places hot key-valued items in DRAM to decrease the reads into Navan for skilled reader workloads, and it uses our proposed RAFL algorithm as its replacement strategy. HDNH develops a fine-grade optimistic concurrency mechanism to enable high-performance concurrent accesses on the multi-core systems. HDNH sets OPMAT and version for each slot of hot table, and the OCF version is used to detect whether there are conflicts between the read and write threads in the corresponding slot. And our experimental setup is as follows. We use app direct mode in AEP, and we use the PMDK package to program in our experiment. We compare the following hashing based index scheme in Navan past level, CCEH and HDNH. The pictures shows the single thread performance, and this figure shows the concurrent performance. Experimental the results shows that HDNH delivers superior performance and high scalability under the various YCSB workloads. The table shows the recovery time of HDNH under the different data size from the 2 million to 200 million. We can see that the recovery time only takes 8.3 milliseconds when the data size is 2 million, and when the data size is up to 200 million, it takes the 400 and 35.1 milliseconds to recover the system. To summarize, HDNH persists keep value items in the non-volatile table while metadatas are placed in the OCF for fast access. HDNH uses hot tables in the DRAM to speed up the storage requests, and it develops a fine-grained optimistic concurrency mechanisms to enable high performance concurrent accesses on the multi-core systems. Experimental results shows that the HDNH delivers superior performance and higher scalability under various YCSB workloads. That's all for my presentation. Thank you for listening.